Physics 11 students, here we are, a brand new lesson, learning about graphing, especially with V versus T and D versus T. So the first thing I just want to quickly review is what do we learn from a graph besides exactly what's written there at a certain time or a certain point on a line? Well, there's a lot we can learn from a graph that's not directly given but indirectly given, and that's typically either given as the gradient or in some cases the area under a graph. So the first thing I want to look at is gradient for d versus t, or distance versus time graph. So you've probably used this term in your life before, rise over run, to calculate the gradient. But what I'd like to suggest is to change your mindset a little bit and start using the terminology the change in y divided by the change in x. And you're going to see why in a moment, why thinking about it in terms of rise over run doesn't really give you the full picture. We're considering it in terms of the change in y divided by the change in x, gives you a bit more insight as to what exactly we're looking for here. So let's take a look at a d versus t graph, and let's draw that out here. So here's our distance versus time graph. We have time in seconds on this axis, and we've got distance in meters on the y-axis. Now the gradient is measured or is considered as delta y over delta x. What we're really looking for is the change in y-axis divided by the change in the x-axis. So in this particular case, what is the y-axis? What does that actually represent for our graph? Well, you can see here the y-axis is going to be distance. So we can say this is the change in distance, or change in displacement, even better, divided by the change in the x-axis. And what is the x-axis? Well, in this case, it's time. Now, by changing our perspective and looking at this as gradient is equal to the y-axis quantity divided by the x-axis quantity, we can see that this is equal to distance over time, and that should be a familiar quantity. So, of course, we know that distance over time is equal to velocity or speed. So when we look at a gradient with distance time graph, we know that the gradient itself is equal to the velocity. And importantly, that also tells us that the velocity is equal to the gradient. And we'll see why that matters when we look at some of the examples below. Now for velocity versus time graphs, let's take a look at this graph again. Let's draw another one here. Oops. Let's draw another one here, I said. Okay, there we go. So this is going to be our velocity and time graph. Now, what is the gradient? Again, we know it's the change in the y-axis divided by the change in the divided by the change in the x-axis. So in this case here, this is going to equal the change in velocity divided by the change in time. And again, this is now a familiar quantity for us. The change in velocity over time is the acceleration. So the gradient of a velocity versus time graph is acceleration. Now, what about the area under the graph? And I guess I should point out a few things. When we look at the gradient of a velocity time graph telling us the acceleration, we can learn a lot from that as well. So this red line here is one gradient. We can see this gradient is lower, meaning it's accelerating more slowly. It doesn't have the same rate of acceleration. And in this case here, we can see that the acceleration is faster for this last line that I've drawn here. Okay, let's take a look at the area under the graph. Now I'm going to make a more simplified graph to kind of demonstrate the point a bit further. So instead of drawing my velocity as an increasing line, I'm just going to draw it as a straight line across. So this is telling me it's a constant velocity. Now what we're trying to find in this problem is the area under the graph. So if this is a velocity time graph, I'm just going to call this v. Whatever value this is, let's say it's 10 meters per second, 20 meters per second. This is our velocity, and this value here, we're just going to call this t. Whatever time it is, doesn't really matter too much. Well, what is the calculation that you could use to determine the area under this graph? So if we're looking at the area under the graph, well, it's a rectangle in this particular picture, and so we're going to see that the one side of it is equal to v, and the other side of the rectangle is equal to t. So the area is going to be velocity times time. And what is a quantity that we know is equal to velocity times time? we don't see this right away, let's think about this equation. Velocity equals distance divided by time. And so if we rearrange this equation, we will get velocity times time is equal to distance. So there we go. So the area under the graph of a velocity time graph is, I'm going to actually be more specific. I'm going to say that this is displacement. And the reason why I really want to be careful in this particular instance is because there are cases when we can have a negative velocity. And so if we have a graph that looks like this, so this is my time and this is velocity. Well, in this case here, this is a negative velocity. And so if we look at the graph here, this would be negative v times t, and so it would be a negative displacement. So just the reason why I wanted to point that out is because you can have positive or negative displacement depending on if the area lies above the axis or if the area lies below the axis. So let's try and put these ideas into practice. So in this case here, we've got a scenario where there's a car at a stoplight and the light turns green, and so it accelerates forward at a constant rate. So when I say constant rate, I mean constant acceleration. You can say constant rate of acceleration. Basically, if it's 5 meters per second squared, that value is going to be maintained for that acceleration. So what I'm going to suggest is I'm going to suggest you do these three graphs. So in a moment, pause the video. But the order that I'd like you to do them in is I'd like you to do acceleration time graph first, then velocity time graph, and then distance versus time graph. I would also suggest that you use pencil if you're doing these directly on your notes. The reason being is that students who are just learning this often do make quite a few mistakes, so please don't feel bad if you make mistakes. So is everyone else who's watching the video at the same time with you. So nothing to worry there, but I would suggest that you pause the video and try doing these in the order of acceleration time graph first, velocity time graph, and displacement time graph or distance time graph. Okay, hopefully you have paused the video and you've come back. Let's take a look at the acceleration graph. Well, this one's definitely the easiest one because this one says when the light turns green, it accelerates at a constant acceleration. So what this is telling us is that the value for acceleration is a constant value. So there's our graph there. Fairly straightforward, just a constant acceleration. Could be 5 meters per second, 2 meters per second. Doesn't matter too much. Now, what about velocity time graph? Now, if you're not sure what to do, take a look at this over here. So what have we learned up here for velocity versus time graphs? We have learned that the gradient of a velocity versus time graph is equal to the acceleration of an object, but also it's important to be able to think of that in reverse and to think about the fact that the acceleration of an object is the gradient of a velocity versus time graph. I know it sounds like I just repeated myself, but it's important that we can kind of translate back and forth between these two ideas. So in this case here, the acceleration at the beginning here is going to be some set value. So that means that the gradient at the beginning is some set value. Now the acceleration is positive, that means the gradient here is positive. Now if I go to another point further down the line, let's say here, well, has the acceleration changed? No, it hasn't. So does that mean, what does that tell us about the slope of our velocity time graph? Well, it tells us that also hasn't changed. And so if we kind of connect all these dots, we're going to see this will be the gradient, this will be the gradient, this will be the gradient, this will be the gradient. And so we should see that it's just a straight line. So we can see that the acceleration is constant, which means that the rate of change of our velocity is also going to be constant. We're going to be increasing and it'll be a straight line. Now this brings me to an important point that what you want to do when you're trying to solve these graphs is you want to pick key points. So if you're not sure where to start, pick some key points on the graph. Now in some graphs it will be obvious what I mean by that, or what you mean by that, in the sense that the graph's going to change at some point as it moves along. And that's definitely a point that you should look at and think, okay, at that point in time, what does the graph tell me? Or what does the one graph tell me about the other graph? So pick some key points. In this case here, I just chose a few points somewhere along the line, the beginning, the end, and this tells me that the acceleration has a certain value, and so the slope of the velocity time graph has a certain value. Now the displacement time graph is where it gets a little bit trickier. But if we follow that same idea that we're going to pick some key points along the graph, well then we should be able to get to our answer with a little bit of thought. So let's pick some key points. And what I mean by that is let's start with the distance at the beginning. Well, we know it's at a stoplight. So we're just going to say that this is our starting position here. So that's the first point, the very, very beginning. The distance is equal to 0. Now at the very beginning, so somewhere down here, we can see that the velocity is very low. So if the velocity is very low, what does that tell us about the shape of our distance time graph? Well, if we look back up here, what we know is that for a distance time graph, the gradient is equal to the velocity. And vice versa, the velocity of an object tells us the gradient of the object, or the gradient of the distance time graph. So if we look at the very beginning here, this point has a very low value of our velocity, which means it's going to have a very low value of our gradient. So at the very beginning, the gradient is going to be a very low gradient. So it starts at 0 and has a low or a very shallow gradient at the beginning because the speed is very low. It's not gaining a lot of distance as it moves forward in time. Now let's pick a different point that's slightly further along. So at this point here, this green point, we know that the velocity is increased. And so what does that tell us about our displacement time graph? Well, it should tell us that that means that the gradient has increased. So at some point further along here, the gradient is a little bit steeper. So let's just draw it around there. Okay, what about this third point? Let's go to the midpoint over here. Why not? So at the midpoint here, we know that the gradient is getting, again, more steep. So I'm going to draw the gradient somewhere here, and you can see that for each of these little sections here, my gradient has gotten steeper and steeper. And this is going to continue. Hopefully you can see the trend by now and see that this is just going to be increasing this way. And if we were to connect all these lines together, well, we'll get a nice smooth curve that looks like this. So whenever an object is accelerating, what we're going to find is that our distance time graph is going to be curving in some way. If it's a positive acceleration, it's going to curve up. So positive acceleration is going to have an upwards curve. You can think of it like a smiley face, it's positive. And if it's a negative acceleration, it will have a frowny face. We're sad because it's a negative acceleration. So the graph is going to have this overall shape. Now at this point here, it kind of starts at this point on here. So we're just going to see the upward part of this over here. Okay, but later on, we're going to see a few more complex cases than that. So remember that the slope of the d versus t graph tells us the velocity, or we can say that the velocity tells us the slope of the distance versus time graph. Okay, that's good. So positive acceleration, positive curvature, or it's curving upwards, negative acceleration, negative curvature, or it's curving downwards. So let's try a few more. So for this one here, constant acceleration, that's going to be these three graphs along the left here. For the constant velocity, try drawing these here. And then for this scenario over here, I'm just going to write something down here. So I'm going to break this one up. It's a bit more complicated. I'm going to break it up into 5 sections. So first section, the vehicle is stopped. The second section, it speeds up. The third section has a constant velocity. The fourth section slows down. And the fifth section, it comes to a stop. Okay, so pause the video here, please, and try these graphs out. In fact, this first one is just like the one, this first set of 3 is just like the one above it. We can get started on that right away. Constant acceleration means a constant slope, which means a constant kind of upwards curvature, like so. And try it the same for constant velocity. This means no acceleration. Okay, so pause the video now and give this set and this set a try. Okay, hopefully you've paused it and you've tried it and you're coming back now to see how you did. So, first part here, constant velocity, that means that there's no acceleration. So the acceleration is 0, so that is done. There stays a flat line there. Constant velocity also means that the velocity isn't changing. So that tells us that it's going to look something like this, some constant value of the velocity. And lastly, we have the displacement. Now remember, as we said before, the velocity tells us the gradient of the distance time graph. So the velocity here is constant and positive, and that means that the gradient is also going to be constant and positive. So every chunk of time, we've gone the same chunk of distance, in other words. So the velocity is constant, meaning the slope of the distance time graph is also going to be constant. Okay, now what about this one? So for a graph like this, remember when I said choose some key points? Well, I'm going to suggest that we follow that advice. So I'm going to break these three graphs. These are all showing the same point in time. I'm going to break them into 5 sections. So this is part 1. I'm going to make this part 2 right here. So this is where it is speeding up. Constant speed will be here. And then slowing down. And finally stop. Okay, let's try this out. So let's look at the very, very first section of the acceleration, or of any of these graphs actually. So it's completely stopped. Hopefully we can see that if it's completely stopped, the acceleration is going to be 0. Also, the velocity is going to be 0. Also, it hasn't moved off the starting line, so the displacement or distance is 0. Okay, that's easy. Now, we've got a scenario where the vehicle has an acceleration, and we're just going to consider this as a constant acceleration. So it went from 0 meters per second squared, now it's got some non-zero value. So from here to here, it's going to be a constant acceleration. And what that means is that, remember, the acceleration of an object tells us the slope of the graph here. So that means the velocity is going to have a constant slope, or constant gradient, because the acceleration is constant. And we also know that if the velocity is increasing, that means the slope or the gradient of the displacement is increasing, which means we're going to get this upward curvature. We can try to draw it there, curving upwards. All right, I kind of accidentally cheated here and told you the next part. So now we have part 3 as a constant velocity. A constant velocity means 0 acceleration. If it had acceleration, we couldn't have a constant velocity because it's a change in velocity. So acceleration again will be 0. The velocity will be a constant value, so a straight line right across there. And what is that telling us about the slope? Well, at this point here, see, we can see just before this line, just before here, and just after here, it has roughly the same velocity value, which means that it has roughly the same value of the slope or of the gradient. So what that means is whatever the slope is at this point in time, it's going to continue with that slope. So we're going to continue that line just in the same direction that it finished off up to this point here. So we're going to have a constant velocity, meaning we have a constant gradient. All right, now step 4, it's slowing down. Well, what does that tell us about our acceleration? Hopefully you recognize that that would mean it is a negative acceleration. So it's going to be slowing down, it's going to have a negative acceleration. And what does that tell us about the velocity time graph? Well, that tells me it's going from a positive velocity down towards 0 velocity. So it's going to be moving this way. And that also tells me what about my distance or displacement time graph? Well, the velocity is decreasing. The velocity is equivalent to the slope of the distance time graph, and therefore my slope is decreasing. So it's going to look like this, and then it's going to start to flatten out. And now for step 5, when it's completely stopped, the acceleration is 0, the velocity is 0, and the distance doesn't change. So it's going to look just like that. Now I know this is a really new way of thinking about these types of problems, so it's completely fine if you want to pause the video and replay that a couple of times until it makes sense to you, or send me an email and let me know, or talk to me on Google Meet on Monday, and I'm happy to answer your questions. I know this is going to be a challenging topic for you to do, not in a classroom, but do the best that you can, and we'll figure out the rest when we come to class. Now, the last thing I wanted to say for this video is the tutorial. So your main homework assignment for this time that you're away is to complete this assignment here. So this is called the PhET Moving Man Simulation. And if you just Google PhET Moving Man, you will find this website right here. So this is called the Moving Man activity or the moving man simulation, it's on PhET, and PhET is a website that does a lot of physics-based simulations. So you can go click the link for PhET, and it'll be on Google Classroom. Click on this, and you'll be able to open up this file, open up this simulation, and once it loads, here we go. In this task here, oh, we're almost ready. In this task here, there's two tabs. There's an introductory one, and then there's a version with graphs. And the version that we're interested in is the version with graphs, because we are going to be trying our best to make the moving man complete these graphs. Now, these graphs tell us on the left-hand side, these are all distance. On the right-hand side, these ones in red, these are our velocity graphs. And we're going to try and replicate these by telling the moving man what to do. So let's take a look at this first graph here. This is our position time graph. And what do we know about our initial position? So we know from our initial position that it's going to be 0. What do we know about our initial velocity? Well, our initial velocity is also going to be 0. So when we open up this moving man simulation and we go to charts, the second tab up here, we're going to make sure that our position is set to 0 and that our initial velocity is set to 0. So these are our starting conditions. Now, if you look at this graph on the right-hand side, or the left-hand side, really, they're both telling you the same thing. This is showing us that the velocity is going from 0 and it's increasing. So what does that tell us if the velocity is increasing? Well, what it means is that we are accelerating and that we have a positive acceleration because the velocity is getting more positive. So what we should put in here for our acceleration is some positive value. Don't worry too I'm going to keep them small-ish. So I'm going to start with 2 meters per second squared. Now, when you try and replicate these graphs, you're going to want to use the play and pause button. So if we go back over here, we're going to continue until the moving man is, say, around this point in time here, which corresponds to this point in time here. So that's when the moving man is around 4 meters in the positive or right direction. And then I'm going to pause it at that point so it's a bit easier to deal with. So let's hit play. And we can see the man is moving to the right. He started with 0 velocity, and he started with 0 position. Started right in the middle. I'm going to pause it here. So at this point on our graph, we can see that we've got the same starting condition. We've got this curling upwards part here, and then we've got this line that has a straight line increasing. And our acceleration is some positive value. Okay, so let's go back here again. Now at this point here, all of a sudden, the slope of our velocity time graph switches to a negative slope. So what does that tell us about our acceleration? Well, remember that the slope of a velocity time graph is our acceleration. So if this is a negative slope, it means that all of a sudden, it's a negative acceleration. So I'm going to change this, and let's go with negative 3. So I've changed the acceleration to negative 3. And let's hit play and watch what happens. So we're going to restart this now, but I've changed the acceleration. So now we can see that the man moves off to the right, he's getting slower, and now he is curling back to where he started. Okay, and this is what we had for our graph on our sheet here. So what the assignment is as follows. You're going to use a sentence or two to describe what the man did in this simulation for the first two. You're also going to complete that description for the third one, but I'm also going to ask you to try and draw your velocity time graph, just a sketch of it, for question 3, and for question 4 to try and draw the position time graph. So if you have produced this graph on the left, if you've done that correctly, then this one should be correct automatically. So you can just copy it right from the simulation, and vice versa with this one. If you've been able to produce this velocity time graph, then your position time graph will be right on screen. You just have to copy it down. So for each of these, just 1 or 2 sentences. So for example, for this first one here, I might say the man started at the origin at rest and accelerated to the right before he started to accelerate to the left. Or you could say something like they're increasing their velocity to the right from rest, and then at some point they start to slow down until they come to a stop, and then they start to turn around. So this part right here would be when velocity is 0. That's when he kind of came to a stop as far as he went to the right and then started moving left. So however you want to describe it is completely fine as long as we can understand from your description what the man in this simulation was doing. So that is the homework, and as always, if you have any questions, feel free to email me. All right, thanks very much.